So last time we were talking about calculating sample standard deviation. And I walked through it, but it was at the end of class. I'm going to walk through it one more time because I doubt any of you remember how to do this. So what do we do? First step in finding the sample standard deviation, what did we calculate? What was the first thing we calculated? Go ahead.
The mean.
Very good. We calculated the mean. And standard deviation is just this measurement of how far away from the mean your data points are. And so what we're going to do is for each of these returns now, we subtract the mean. And then that's your deviation. Now, if you added all those deviations together, they would sum to 0. So we can't just talk about the average deviation. It would be a meaningless measure. And besides, we don't care plus or minus. What we're concerned about is how far away these things are. Two ways to get rid of a negative sign. One is absolute value, and the other is by squaring it. And standard deviation chooses to do the squaring thing. So we're going to take those deviations, we're going to square them, and then we're going to add them together to come up with something called SSD. What do you think that stands for? Sum of squared deviations. Nice try. Sum of squared deviations. Now, how do we find the variance? We're going to take the sum of squared deviations and divide by 1 less than the sample size. Now, you say, why 1 less? In sample statistics, we had to use some of the information from the data set in order to calculate that mean. Remember, that's the first thing we calculated. And statisticians tell us that using up that information from the data set reduces our degrees of freedom. What is a degree of freedom? Ask your statistics professor. All I know for sure is basically this means that we have to divide by a smaller number to get our variance. Now, once we get variance, how do we get from there to standard deviation? Ms. Rafael, how do I get standard deviation from variance? Swing and a miss.
Square?
Square root.
Oh,
Yeah, we're going to take the variance and get the square root. Thank you. Okay, so let's walk through one more time how we do this thing in the calculator. So we're going to pull up the calculator, and we are going to start with, oh, by the way, are we going to work up and down, or are we going to work across? Yeah, we're going to work across. Makes your life so much easier. Are we going to write anything down and then type it back into our calculator? No. So there are chances for rounding error, there are chances for mistyping, miswriting, all sorts of crap that can cause you horrible, horrible pain. So we're not going to do that. So I'm going to start here with 0.137 minus, let's see if it remembers the mean from last time. Oh, it does not. So if you remember, the mean was 0.2144, and I had that stored in location 0. So 0.137 minus, recall 0, equals. Does that look right? That's our deviation. What's the next step? Got to square it. Use this button right here. Now, what should I do with that number? Store where? 1. Very good. Okay, now 0.358 subtract, recall 0. What should I do with this number? Square it. And then what do I do? Store 2. Very good. And then we've got 0.4514. What do I do next? Subtract what? Recall 0. Very good. And that gives us this deviation. What do I do next? Square it. And store where? Very good. Store 3. Clear. Can anyone tell me, Mr. Rosen, can you tell me what the next thing we need to do is?
Would be we're doing the negative 0.088.
So 0.0888, and then what button do I have to hit?
Plus minus.
Yeah, so it's weird, it's after, right? And then what am I going to do?
Minus.
Minus what?
Minus recall 0.
Very good. And then that gives us this. What do I do next?
Store 4.
Ooh,
Square.
Square. And then store 4. Store 4. Okay. Now, how do I get the sum of squared deviations, Ms. Black? Yeah, so recall 1 plus recall 2 plus recall 3 plus recall 4 equals. Now I have the sum of squared deviations. How do I get variance from here, Mr. Poloski? What do I divide by?
Degrees of freedom.
Degrees of freedom. In this case, how many would that be?
3.
Yeah, so he's taking the sample size, subtracting 1. And there we go. Now we have the variance. Ms. Knight, how do we get from variance to standard deviation?
Square root.
Yep, very good. And there we are. So that is the easiest method to use the hard way to get the standard deviation. Would you like to know the easy way? Okay, so let's talk about how to get the easy way on your calculator. Start out with second and the number 7. What does the number 7 say above it? Yeah, it says data, and we are going to use this to enter this data to do some statistics on it. And so the second thing that I want to do here, though, is second and then hit the clear button. Because if we don't, it'll most likely remember the last thing we did. And let's say our previous example had 5, sample size of 5. Well, that 5th one's going to be hanging out there, and it's going to make your life a living hell. So you always want to clear it out, because your calculator will remember things you did years ago. Okay, so we're going to start out here with x1, 0.137. Enter. You got to hit enter, or it's like it never even happened. Then we're going to arrow down. It turns out that your calculator can think about 2 stocks at the same time. And it could give us some other information. But for right now, all we're going to be doing is dealing with one series. So I'm just going to leave that y as it is. Then I'm going to arrow down. x02. What do you think I'm going to put in here, Mr. Ali?
The second.
Yeah, 0.358. What button do I have to hit to make this work?
Enter.
Enter. And then we're going to arrow down. What do I do here? Yeah, I just leave it. x03, 0.4514. Enter. Arrow down. What do I do here? Yeah, leave it. And then, Ms. Minahan, what do I do here?
I do 0.0888 plus minus.
Uh-huh.
Enter.
Very good. Okay, so now I have all the data in, but what I like to do is go back through it and make sure that it's all in there and they're correct, because there's a chance that you forget to hit the enter key. There's also a chance that you might mistype something, so always check your work. It saves you so much time. So now we're going to hit second and the number 8. What does the number 8 say above it? Stat. What do you think stat is short for? Statistics. Now, when you do that, it says LIN, which is either some Chinese person's name or the beginning of the word linear, because linear statistics, something like that. We're not going to be concerned about what that means. Here's what we're going to do. We're going to hit arrow down. It says n is equal to 4. What do you think n is? Yeah, it's a sample size. Is that correct? This is another way to check your work, right? Because if n said n equal 5 or 6 or 7 now, we would know we forgot to clear it out. So then we're going to arrow down. It says x bar is equal to 0.2144. What do you think that is? Yeah, it's the mean. It's the sample mean. The sample mean. And then we're going to arrow down. S of x. What do you think that stands for? Yeah, it's the sample standard deviation. The sample standard deviation, which is what we calculated earlier. By the way, does that number look familiar? Yeah, it's the same thing. Now, what if on an exam, by the way, the calculator doesn't give you variance. What if on an exam I ask you for variance? What button could you hit on your calculator right now? Square. Yeah, that's all you got to do. And there you go. Now you've got the variance. And actually, you've got one more decimal place than is showing on the slide. That's great stuff, and we leave all the numbers in the calculator. It just works really well. Okay, so now here's what you need to know. 2 things you need to know. If you want to get back to standard deviation, by the way, how do we know this isn't standard deviation? There's no equal sign. There's no equal sign. If we go up and then come back down, you'll see now there's an equal sign and the standard deviation is there. So if you get rid of it accidentally, you can always up and down and you'll be right back where you started and you'll be good to go. Now the second thing is I'm going to show you something here. I'm going to show you something and I'm going to tell you never to use it. I'm going to tell you never to use it. Unfortunately, one or two of you will. And it's really boils down to this. When I was a little kid, my mom said, "Don't touch the stove, it's hot." What do you think I did? Yeah, I touched the stove. I don't have fingerprints on this hand. Okay, so, I'm kidding, I have fingerprints. So, it's just human nature. I don't know why. But I'm going to show you something here, and I'm going to tell you to stay away from it. And then when things go horribly wrong for you, I'm going to say, "I told you not to do that." So here we go. Are you ready? Sigma sub x. Sigma sub x. What is sigma compared to s? Yeah, it's population standard deviation. Now, what we are doing in chapter 10 is all sample standard deviation. Some of the stuff that we're going to mess around with in chapter 11 is going to be population standard deviation, but we will not be using this calculator for that kind of stuff. So you will never, 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 never use this in my class. You will never use this in my class. You will never, never, never use this in my class. Don't use this in my class. Should we use this in my class? Absolutely not. Very good. Thank you. Okay. Now, I think that's all I want to say about that. By the way, what's the difference between sample standard deviation and population standard deviation? Well, if so I've got this whole population here. I've got 18 students. I guess we're missing 2. So I've got 16 people here. I could pick out a small subpopulation. Let's say the 3 people in this corner. And we could figure out some things maybe about the group as a whole. But we would have some errors there. Number 1, what is the assumed gender of these 3 people? Male. If I said, "Oh, hey, everybody in class is male," would I be correct? No. I could also say 2/3 of our students here are from international locations. Would that fit the rest of the class? No. And so those are sample problems, and that's why with this sample variances tend to be higher because we have less information. You got to be careful with them. Come on. But with population, in theory, we know everything. How often do we actually know everything about the entire population? Almost never. Think about China. They got like 1.4 billion people. If they went through and figured out everything about everybody in China, by the end of doing that, are they going to have correct information? No, because in the meantime, people are going to do one of 2 things. They're going to get born or they're going to die, right? And so population standard deviation, very hard to come by. Sample standard deviation is what you're going to see a whole lot more. Questions? Okay. Now, by the way, this YouTube video shows you how to do this TIVA 2+ thing. So now we're on to the normal distribution. And remember, we said that we think the stock returns are normally distributed. There are a couple of things that we know one for sure, and we strongly suspect the other one, that makes it not quite perfectly normally distributed. First of all, with a perfect normal distribution, it goes on forever in both directions. And while potential returns are theoretically infinite, what's the lowest a return can ever be? Everybody wants to say 0. Oh my goodness, I wish that were true. My portfolio would still be worth more, right? So you can have negative returns, but can you ever have more than negative 100%? No. Remember, limited liability makes stocks where they don't go below 0. So the most you could ever lose, the lowest return you can ever have is minus 100%. And so we know the distribution is truncated at minus 100%. There's thing number 1 that makes us know that stock returns are not truly normally distributed. Number 2, we looked at the populations of returns over the years from 1926 to present, and we see that this distribution has fat tails. What do you think fat tails means?
Goes out longer.
It doesn't go out longer, but, because remember, theoretically infinite in either direction. But we do, go ahead.
I forgot the term, but it is flat tail means the size is higher in the.
Oh, okay, so I think you're thinking about skewness.
Yeah, yes.
Okay, so here's what's going on. Theoretically, we're going to see that there should be a certain proportion of all these observations in different parts of this distribution. And plus or minus 2 standard deviation, we're going to see 95.44% is contained in there. If you've got fat tails, you've got more observations in the tails than should be there in accordance with the normal distribution. And so you'd have fewer than 95.44% of observations between that plus or minus 2 standard deviation than the normal distribution would say that you should have. So that's what we're talking about. Now, am I going to make you do anything with those 2 pieces of knowledge? Absolutely not. We are going to, for the sake of this class, assume that stock returns are normally distributed. And by the way, once again, statisticians are really mad at people like me because we think we can apply statistics and they think we have a small population of data. And by the time we get enough data to satisfy those people, I will be dead. And so we just have to make an assumption and go with it. Okay. Now remember, there were 2 numbers that we said that you could use to totally define the normal distribution. What were they? One of them your grandmother could calculate. What was it? Yeah, the mean or the average. That's the first thing. And so that's going to be in the middle. That's the mean. And then, what was the other one? I'll give you a hint. We just got through calculating it. Yeah, standard deviation. So if I know mean and I know standard deviation, I can totally generate the normal distribution. Now you say, whoopee, what does that mean? The normal distribution is an amazing thing. And it doesn't just apply to finance. This thing shows up everywhere. So I'll give you an example. We'll start with an example that you might be familiar with. How about IQ? What is IQ? What does it stand for? Anybody know? What do you think the I stands for? Intelligence, and the Q is quotient. The Q is quotient. And by definition, so here's how IQ starts out. There's this French guy, and he gets a bunch of French kids together, and he gives them these smart tests. And then he labels the average as 100. And then he looks at the distribution from there. Okay, and so what this French dude figured out was he's defining 100 as being the mean. So that's going to be in the middle here. But what he figured out is the standard deviation for intelligence is 15. 15 is the standard deviation for intelligence. So now we have 2 things. We could totally show up or determine this normal distribution for the intelligence of the population, assuming we're all French kids, right? Okay, so we can tell certain things. First of all, we know that with anything in the normal distribution, that between minus 1 standard deviation, and by the way, they're using population standard deviation symbol here, we're using sample. Between minus 1 and positive 1, we have 68.26% of the observations. So if I want to know what is the percentage of people between 85 and 115 IQ, the answer is 68.26% of the population. Does that make sense? Okay, now, how did I get 85 and 115? Yeah, it's mean minus 1 standard deviation, so it's 100 minus 15. And then it's 100 plus 1 standard deviation, or 115. And so that's how I got those 2. Now, can anybody tell me what percentage of observations we would expect to be between 70 and 130? 95.44%. 95.44%. And then if I said what percent of the population falls between 55 and 145, what would you say? 99.74%. By the way, let's talk about, these are the exact numbers. Let's talk about the approximation. I'm a lousy artist, but you guys have already figured that out. Okay, so here's the mean. And then we have plus 1 standard deviation, plus 2 standard deviation, plus 3 standard deviation. I know that looks like a 36, but so here we have minus 1 standard deviation, minus 2 standard deviations, and minus 3 standard deviations. So if I look at plus or minus 1 here, typically we just call that 68%. So if you're getting not quite perfect numbers on your multiple choice, that's why, because we're using these approximations. In fact, I believe almost all, if not all, of the homework and test questions use the approximation. By the way, this needs to be on your note sheet because I'm not going to give you this information during the exam. Let me say that again. This needs to be on your note sheet because I'm not going to give you that information during the exam. Okay, now, on plus or minus 2, if we round that to the nearest percentage, what do we get? 95%. Okay, and then if we say plus or minus 3, if I take it to the nearest percentage, what do I have? High gratitude, it'll be 100. If we do that, that's no fun. It leaves those tails. There's nothing left in the tails for us to do calculations with. So instead, what do we say? We say 99%. Okay, so you should have this on your note sheet. You should have this on your note sheet. You should have this on your note sheet. Now, I'm going to tell you a quick story here to hammer this home. I had a lady, and it was a China EMBA class. She was actually from Inner Mongolia. I don't know if you know the Mongolian people. They at one point ran half the world, right? They're very, very tough, very strong, and very strong-willed. And this lady, she calls me up during the exam, and it's the problem says, what is the percent chance of, and it gives some other stuff. And she says, you didn't give me enough information to solve this problem. And I point at her note sheet and I say, yes, I did. And she looks at me, she says, no, you didn't. And I said, yes, I did. And then she says, no, you didn't. And she grabs for my lapels. No kidding, true story. I jump back. She narrowly misses pulling me over the table. Why do I tell you that story? Because when you're taking the exam and you're like, wow, I'd like to pull Dr. Haggard over the table because they don't have enough information, I want you to remember to look at your note sheet for this. Now, at the end of that story, she and I are still good friends on WeChat. This has been like 15 years ago. So, you know, all's well that ends well, right? She still doesn't hate my guts. Okay, now let's go back and we're going to work some thoughts, some problems here on IQ. And then we'll switch over and we'll start talking about returns. Remember that for IQ, X bar is equal to, what did I say it was? 100. And what did we say sample standard deviation is? 15. Now, by the way, why is it sample standard deviation? Did that French dude look at every single person on the face of the earth? No. Okay. Now, here's what you need to know. Anytime that we are asked a question about a number, we're going to figure out how many standard deviations away from that how many standard deviations away from the mean that number is. And we're going to use something called T. You may have heard of T-scores before. It's very similar to Z. Okay, so we're going to say, take that number, subtract the mean, and divide by S sub x. And this is going to give us the number of standard deviations away from the mean. And it's going to be either positive or negative or 0. Okay, so if I ask you, what is the percentage of people who have an IQ of 115 or below? Here's how we'd start out on that. We'd say 115 minus 110 divided by 15 is equal to plus 1 standard deviation. If we're going to locate that on this distribution, we just come right here, it says plus 1 standard deviation. Now, how do I find out the probability that someone's IQ is 115 or lower? Well, I know a couple of things. Number one, I know that the normal distribution is symmetric. What does symmetric mean?
What happened to what's that happened to?
Yeah, it's basically mirror images, right? Okay, and the second thing that I know is that the total probability under the distribution is how much? Ooh, under the whole thing. Close. Yeah, under the whole thing's 100. Plus or minus 3 is 99, right? Okay, but this thing, remember, it goes on forever in both directions. Okay, so now I've got, I know that I'm plus 1 standard deviation. I know that everything to the left of the mean, if this whole thing is 100%, what is everything over here? What percentage is that? Yeah, it's 50%, right? And then I also know that this other half, 68.26%, is evenly divided between minus 1 standard deviation and plus 1 standard deviation. I know that bit is symmetric too. So, what percentage falls between 0 and positive 1 standard deviation? Yeah, 34. Let's just use the average, or the approximations here. 34. So I've got 50 plus 34 gives me how much? What's 50 plus 34? 84. So the answer is 84% of the population has an IQ of 115 or lower. Does that make sense? By the way, can I say, what's the probability that someone has an IQ of 115? No. We were talking about greater than, less than, or between. We never do what's 127. We don't do that. Can't do that. Because in theory, at that one tiny infinitesimally small point, the probability is near 0. Okay. Now, back to the story. What if I said, what is the population, or what is the percentage of the population that has an IQ higher than 70? Higher than 70. So we would start out with 70 minus 100 divide by 15. What does that equal to?
Negative.
What's the sign?
Negative.
Yeah. Minus 2 standard deviations. Okay, so if I ask what's the percentage of the population that has an IQ higher than 70, we know we're talking about down here at minus 2 standard deviations, and we know a couple of things. Number one, what is the proportion of the people that are at the mean or higher? It's 50%, right? What is the percentage of the population that is going from the mean down to minus 2 standard deviations? How would I find that? 95 divided by 2, which I think is what, 47 and a half? So if I add 50 and 47 and a half, I get 97.5% of the population is smarter than 70. By the way, if you've ever wondered where some of the terms that we use come from, it comes from this IQ study. They actually used the plus minus 1 standard deviation to start naming different groups of people. And so if you are at 100, you are average. And then I don't know what 115, I think 130 is called gifted. And if you've got 145 or more, guess what? You're a genius. You're a genius, right? Plus 3 standard deviations above the mean, you're a genius. And we've got it going the other way. Now, these were all clinical scientific terms when they first got trotted out. Now they've got bad associations with them. But I can tell you this for sure, minus 2 standard deviations, IQ of 70, was considered to be mentally retarded. That's a clinical term. But since then, because people used it in a bad way, it's taken on bad connotations. But it's standard deviation is how these things were demarcated. Okay, now let's see. What if I ask you what proportion of people have an IQ that is not higher than 85? What if I said, what's the average proportion of people whose IQ is not higher than 85? Well, the first thing I'm going to do is say equal 85 minus 100 divided by 15, that's going to be equal to what?
-1.
Yeah, minus 1 standard deviation. Now, notice I said not higher than. What's another interpretation of not higher than? Is less than. And so what are we actually looking at? We're going to look at over here to the left-hand side of that minus 1 standard deviation. So, how would I figure out what percentage of the population is below minus 1 standard deviation? Any ideas?
Yeah, we could do like 100 minus, that's standard, whatever the negative standard.
So 100 minus 68.26.
32%.
But there's one other thing here. Remember, we've got two tails, and this thing is symmetric. Yeah, so we got to divide by 2, right? We got to divide by 2. And so the answer would be 16% of the population has an IQ lower than 85. Now let's walk through that one more time. I'm trying to look for this tail over here. That's -1 standard deviation down. And what I got to remember is that that 68.26 is right out of the middle. And anything that's not in that 68.26 is symmetrically represented on both sides. So when I take 100 minus 68, that actually represents the area for the two tails. Thankfully, the tails are symmetric. So all we have to do is divide by 2 and figure out that we've got 16%. Okay, now let's do another little experiment here. Let's say that you are a genius. You have an IQ of 145. And my question to you is, what percentage of the world population is smarter than you? So let's do the math here. 145 minus 100 divided by 15 is equal to plus 3 standard deviations. Okay, so we know that basically 99%, in fact, let's use the exact on this one. 99.74% are between those two. And so we know that the tails add together to be 0.26%. But what do I have to do? Yeah, I got to divide by 2 because that's both tails. And so that tells me that 0.16% of the world, 0.13% of the world population is smarter than you. Do you feel pretty good right now, knowing that only 0.13% of the world population is smarter than you? So let's find out what that really means. Get your calculator out. Get your calculator out. And I want you to type 0.0013. 0.0013. And then I want you to multiply it by 8, followed by 9 zeros. 8 followed by 9 zeros. Why are we putting in 8 followed by 9 zeros? What does that represent? That's the population of the world. Okay, what is 0.0013 times 8 followed by 9 zeros? How much? Okay, did you guys hear that? How smart do you feel now? That's how many people are smarter than you, right? Millions of people. You're a genius, and millions of people are smarter than you. Now, the good news is a lot of those folks are in areas of the world where they don't have electricity or internet, and so you'll never have to compete with them. So there's probably 4 million of those. So it's the other 6 to 8 million you have to worry about. Does that make sense? Okay. Now, we have kind of beat this thing to death using IQ. Let's talk about stock returns. And the stock returns the data that we're using here is for large stocks. So if you remember large stocks, we have a mean of 11.8%. And that's going to be right there in the middle. And then the standard deviation. Looking at the numbers here, can anyone tell me what is the standard deviation that we're looking at? How'd you get that?
I just subtracted 8.7 from 11.8.
Ah, but can you do that? Wouldn't it be 11.8 minus 8.7?
Oh, right, got it.
Okay, I'll give you an easier way to do this. Why don't we take 32.3 and subtract 11.8? 20.5? Sound right?
Yeah.
Okay, and then if we did 11.8 minus 8.7, I believe we would also get 20.5. Is it 20.5? Yeah. Okay, so now we know the standard deviation is 20.5. And so if I ask you, let's see, I'm going to erase some of this stuff. If I ask you, what percentage of returns do you expect to be greater than minus 8.7? Let's make this even harder. What's the probability that you will not lose more than 8.7%? What's the probability you will not lose more than 8.7%? First thing to do, notice the word lose. What's the sign on this thing? Negative. Does that make sense? Lose is negative. So T is equal to minus 8.7 minus how much? 11.8. Because that's the mean. And what are we going to be dividing by? Yeah, 20.5. And so this is minus 1 standard deviation. And so we're looking for the probability that you will not lose more than 8.7%. Is that this part over here, or is it this part over here? Yeah, it's over to the right. The probability that you won't lose more than. And so we're going to take this and we're going to say, so what percentage of points are greater than minus 1 standard deviation? Well, we know that greater than the mean is 50%. And we know that between plus and minus 1 standard deviation is roughly 68%. So how much of that is between 0 and minus 1 standard deviation?
14?
Yeah, 34.
Yeah.
34. Okay, so how then do I just add these things, right? The 50% that's above the mean, and then the 34% that's between the mean and minus 1 standard deviation. I add them together, and I get 84%. Now, I can work this the other way, the way that you were doing it in your head, and that is I could say what percentage of the observations are actually not in this set. And I know that tail is 16%, and I could take 100% minus that 16% and come up with exactly the same answer. There is more than one way to solve all of these problems. Do I care how you do it? Absolutely not, as long as you get the right answer. I don't care. Questions? Okay, what is the probability that returns will be between minus 29.2% and 52.8%? This one's easy, just softballing it.
95.
Yeah, 95%. And so we could play this game all day, just like we did with IQ. So the big things to look for is not more than, and lose, and between. Another one, I could say, what is the 95% probability range for large stocks? And you would tell me, well, it's between minus 29.2% all the way up to 52.8%. That might be another kind of wording that you would see. I have an entire video set of examples on doing this. I guarantee you, right now you're feeling pretty good about this stuff, hopefully. But as soon as you walk away, when you start trying to work on stuff, you will be confused. And so what I would tell you is, before you start working on things, watch this video we're making right now, and then also watch the video examples that I posted on Blackboard, and that should put you in pretty good shape to start doing the practice and the homework. Questions? Okay, so we're going to move on from the normal distribution now, and we're going to talk about average and arithmetic and geometric average. The arithmetic average is the one that your grandma knows about. If you've got 5 different numbers, you add them together and you divide by what? 5, right? Same, so the number of numbers. It's really easy. Now, I can do that with stuff in percentage. I can do that with stuff as decimals. Doesn't matter one bit. If I put in everything as percentages, my average is going to come back to me as a percent. If I put in everything as decimals, my answer is going to come back to me as a decimal. The next one is not that way. When we use geometric average, we have to use the decimals. Make that note. When we do geometric average, we have to use decimals. We have to use decimals. Okay, now, it's kind of freaky. The first thing that we're going to do is we're going to start out with our decimal returns. And to each one of them, we are going to add 1. And so basically 0.05 for 5% becomes 1.05. So we're going to add 1 to all of our returns. And then we're going to take those 1 plus return terms and multiply them all together. And how many of those are we going to have? If we've got 5 return samples, then we'll have 5 of those terms. If we have 3, we'll only have 3. That's the second step. The third step is to take that product to the 1 over n power. What is n? Yeah, then it's the sample size, right? It's the number of these samples that we're looking at. If number of observations. If we were looking at 5, this is going to be to the 1/5 power. If we were looking at 9, it's going to be to the 1/9 power. And then at the end of that all, remember in the beginning we had to add 1 to all these things? Now at the very end we're going to subtract 1. But keep in mind the return that we get here is going to be in decimal form. The return that we get from this formula is going to be in decimal form. If I'm asking you to tell me the percentage, what are you going to have to do? Yeah, I got to multiply it by 100%, right? By the way, multiplying by 100% is exactly the same thing as multiplying by 1, which algebra tells us is totally legal. So we have not broken any laws here. Okay, now let's see what we've got next. So here's our simple example. Has everybody gotten this down? Okay. We have a portfolio, and we are given values for it at time 0, 1, and 2. At time 0, it's worth 100. Time 1 is worth 50. And time 2, it's worth 75. Next, we're going to figure out the return. Now, in order to calculate return, you always have to have the previous number. So in order to figure out a return for time 0, we would have to have time -1. We don't have that, so there's not going to be any return here. Can we figure a return for the time between 0 and 1? Yeah. So 50 minus 100 divided by 100. Remember, it's p sub t plus 1 minus p sub t divided by p sub t. So it's 50 minus 100 divided by 100. What is that? Negative. How much? 0.50, right? Okay. Pretty good. Now we're going to look for the return between time 1 and 2. And we're going to start here with 75. We're going to subtract 50. What does that give us? So 75 minus 50 is 25. Divide by 50. What's 25 divided by 50? 0.5. 25 divided by 50 is 0.5. Okay, now, if I were to look at this thing and ask, what is the arithmetic average return? It'd be pretty easy. I'm going to add this and this, and I'm going to divide by 2. What is this plus this? 0. What's 0 divided by 2? 0. And so the average arithmetic return here, or the arithmetic return, arithmetic average, is 0. Now, let's think about that. Does that smell right to you? We started out with 100, And we end up with 75. Does that really feel like we have zero return? No. So let's take and go through this using our geometric return. What is 1 plus negative 0.5? It's just 0.5, right? And what is 1 plus 0.5? 1.5. Okay, so here's what we're going to do to get the geometric average. We're going to take 0.5 times 1.5. That's just the 1 plus R1 times the 1 plus R2. And now we're going to take it to the 1 over n. What's n? 2. And then we're going to subtract 1, and then we're going to multiply that whole thing by 100%. So let's get our calculators out and give this thing a shot. And I'll show you how to do that 1 over n. First thing we're going to do is our inside 0.5 times 1.5 equals 0.75. So that's everything inside the square brackets. Now, those of you who are mathematically enhanced may realize that 1/2 to the 1/2 power is square root. But we're not going to use the square root button because it's not always going to be 2 for n. What if it's 9? You need to know another way. So here's what we're going to do. I want you to look at the button immediately above the number 9. What do you see? Y to the x. So we're going to raise this thing to the x power. What's the x power going to be? I'm going to open parentheses, 1 divide by 2, close parentheses, equal. And so that's everything right here. That's everything right here. Then we're going to subtract 1. That gives us minus 13, minus 0.13. What's the last step? Yeah, times 100 to get it in percentages. Okay, so we're looking at minus 13.397%. Does that pass the smell test a little better? Yeah, so if I was just looking at this really simplistically, thinking we're going from 100 down to 75 over 2 years, I would expect that to be somewhere in the neighborhood of 12.5. And here's why. Because we're losing 25% over 2 years, 25% over 2 years divided by 2 gives me 12.5%. Just a rough approximation, but it helps me to stink test that number. Now, how can I prove to you that that is the actual return? We're going to use our calculator. Second, clear TBM. I'm going to treat this thing like a future value. I'm going to treat this thing like a present value. And so I'm going to put in 100 negative present value. And I'm going to put in 75 positive future value. Why do I put different signs on those things? Yeah, cash flows in opposite directions, right? Got to have opposite signs. Could the signs have been reversed? Absolutely. Okay, how many years are we looking at here? 2. So I'm going to hit 2n. And then I'm going to compute I per y. Does that number look familiar? Yeah. So here's what's going on. The geometric average takes compounding into account. The geometric average takes compounding into account. Your financial calculator, the TVM keys, takes compounding into account. And so if you've got a very simple problem like this with no dividends or anything intervening, then it's very simple. You could just use your TBM on your calculator. On the practice and on the homework, I will also throw in dividends. But I've created a video that you can go out and watch that walks you through step by step the simplest possible way to do that. And I could save you a lot of time, pain, and suffering. And I've developed that method over, say, 10 years, and it really works. It's the easy way to go. Okay, any questions so far?
If we had, so like 100 is the first value we're using. If we have a time before 1, Would we just use that for present value instead?
Yeah, if we were gonna, so let's say we had a -1 up here, we could have figured a return here, and we would have called the initial value, present value, the ending value, future value, and how many would we do for n at that point?
3.
Yeah, 3. Does that make sense? Good question. Okay, now, Mr. Murs, you look a little uncertain. Are you okay?
Why was it 3?
Because he's asking, what if we had another year's values? What if we had -1? What if we had -1 and it was 120? Then what we would have done is had 120 be right here, and then we would have 1, 2, 3 years. Does that make sense? Okay. Now let's talk about when we're going to use each of these. First of all, anytime you're calculating a statistical thing, like standard deviation, we will always use the arithmetic mean. Let me say that again. Anytime you're going to be doing something statistical, you always use the arithmetic mean. Anytime we're going to be doing something with a normal distribution, we always use the arithmetic mean. Anytime we're going to be doing something with a normal distribution, we're going to be using the arithmetic mean. The geometric mean is only used when we are trying to examine the value of the impact of compounding. When we are trying to examine the impact of compounding, then we look at geometric. And it turns out these things answer different questions. So arithmetic average answers this question: what was your return in an average year over a particular period? What was your return in an average year over a particular period? So over this 2-year period, what was your average return for a year? It really is 0, right? Because we have a return of -0.5 here, and we have a return of +0.5 here. It really is 0. But geometric answers this question: what was your average compound return per year? What was your average compound return per year over a period? Now, I'm gonna tell you something about the relationship between geometric average and arithmetic average. The arithmetic average is always greater than or equal to the geometric average. The arithmetic average is always greater than or equal to the geometric average. Now, the only time that they're equal is if all the returns are identical. So if we'd had 5%, 5%, 5%, 5%, 5%, then both the arithmetic average and the geometric average would be 5%. But as soon as we start to introduce some volatility, some variation in here, if the standard deviation goes greater than 0, now what we're going to start to see is this geometric average falling away from the arithmetic average. It's going to go lower and lower. And the crazier this thing gets, the bigger that standard deviation, the bigger the difference will be between these two measures. And so let's get our calculators out and figure this out. So let's, first of all, we'll say, what if I've got 0.08? If so I'm going to have 4 years in a row of 0.08. I'm going to multiply by 4, and I'm going to divide by 4, and that tells me my arithmetic average is 0.08. And keep in mind, they're all 0.08. So now, let's talk about what if I do the geometric average. 1.08 times 1.08 times 1.08 times 1.08. Is that what you guys are getting? Okay, now I'm going to take that to the 1/4 power, because there are 4 returns. So I have y to the x, open parentheses, 1 divided by 4, close parentheses, equals. I'm getting 1.08, I'm gonna subtract 1 and multiply by 100%. And in this case, just as we predicted, the arithmetic and the geometric are the same. Now, what if instead of that, our returns were 6%, 10%, 6%, 10%? Your arithmetic average is still going to be 8%. If you don't believe me, you can do the math, but it's 0.32 divided by 4 gives you the same thing. But what about our geometric average? We would be saying 1.06 times 1.10 times 1.06 times 1.10 equals. What am I going to do next to get the geometric average? What button do I hit? Yeah, the Y to X. And then what button do I hit next? Ms. Benioff? Open parentheses. And then I'm going to say 1 divided by what, Ms. Roll? 4. Very good. Close parentheses. Equal. And so then I'm going to subtract 1. I'm going to multiply by 100. Notice that our geometric average came out to be less than the arithmetic average. I could have made it even crazier. What if I'd made it 12 and 4, 12 and 4? Then this geometric average would have been even further away from the arithmetic average. And so we say that for arithmetic average, because of this fact, we say it's probably too high if we're just going to use to try to estimate an average return. And if we talk about geometric average, we say it might be too low for that reason. So there's actually a formula in your book on how to come up with this weighted average, blah, blah, blah. No one uses it, so I'm not going to make you learn it. But you need to know that basically arithmetic average may be too high, geometric average may be too low. And then we say that the arithmetic average may be too high for longer periods, and that geometric may be too low for shorter periods. This one's a little more complex to explain. So I'm going to give you one of two choices here. Either one, you can accept this as fact, and you can just write this on your note sheet for both of these. Or number two, I have an academic paper posted out there that goes into great detail on why this is. If you want to know the great detail, feel free to go out there and read the academic paper. More power to you. But if you just want to do well on the exam, I just put this on your note sheet, right? Is it so hard? Just put it on your note sheet. Questions? Okay, so that's the end of chapter 10. I don't want to waste 14 minutes here, so I do want to get into, we'll just talk about chapter 11 and get some basics down. So far, what we've talked about are individual securities. Remember, chapter 10 is risk and return of individual securities. And so all I'm concerned about is how the return is acting on that one security. That's all I care about. Now, it turns out if I'm holding more than one security and they don't follow exactly the same path, something interesting happens. So, by the way, this is one of 3 times in the class that I'll do interpretive dance. Are you ready? Okay, so what if we had 2 assets? And if they move perfectly together, then it's not going to look any different than if they were the same individual security. Nothing has changed. But what if they don't? What if, when this one goes up, this one goes down? And so now, let's say I've got a portfolio of 2. By the way, a portfolio is just a collection of assets. That's all it is, a collection of assets. So I've got this collection of 2 assets. And when one of them goes up and the other one goes down, the return for the portfolio kind of evens out between the 2 of them, right? And then later on, they swap. And so it starts to look like this, where these things are moving kind of in opposite directions. Now, each one of those things is going to be fairly risky by itself. But when I put those 2 things together and come up with the average return for the portfolio, something amazing happens. It looks more like this. It's smoother. It's less risky. That's diversification. That's why we hold portfolios. By the way, can you tell if something is going to totally go up? No. Can you tell if something is getting ready to just totally go down? No. You can always be fooled. And none of us are really smart enough to be able to figure that out. It will require you to be able to predict the future, and you can't, right? Okay, so what does that mean? It means what we need to do is have a variety of assets that are going to do better in some circumstances and worse in others, because what we want to do is try to smooth out our overall returns. I will tell you a quick story about a man that I worked with. This is right at the end of the dot-com boom. His name was Kenneth. And Kenneth, like me, sold plastic pellets. And Kenneth would come into the office every day, and he would tell us what his portfolio was worth. Remember, portfolio is a collection of assets. And he says, yep, my portfolio just broke $2 million today. Now, that was big money back then. Probably still big money to you guys because you have somewhere between jack and squat, right? But that was big money back then. And he would come in and he would say this, and he would be like trying to rub it in that he's got so much money. Now, Kenneth was 62 years old. So what do you think he's planning to do with that $2 million? What's his goal? Yeah, retire. Okay. Now, and he did that time and time again. And I said, okay, Kenneth, what are you invested in? He says, internet stocks. I said, internet stocks? He says, yeah, 100% internet stocks. And I said, Kenneth, that's crazy. He's like, no, man, you're crazy. I'm rich, right? Do you know what happened? I mean, there's a reason we call it the dot-com bust. But do you know what happened? The value of all those internet stocks went straight into the toilet. Kenneth came, and then after it started falling, he came into the office. I'm like, hey, Kenneth, what's your portfolio worth today? Oh, by the end, he hated me, right? But I had to listen to his $1 million speeches all for like 6 months. Okay, so the last number Kenneth threw out was $100,000. He'd gone from $2 million in assets down to $100,000. Now, if Kenneth had owned a diversified portfolio that contained more things than just internet stocks, do you think his portfolio value would have fallen so low? Absolutely not. Now, my portfolio was down too, but it wasn't down like that because I wasn't invested 100% in internet stocks. And so that's why we start talking about the value of holding things in a portfolio, is because we're going to get to this idea of diversification. Let's talk a little bit about vocabulary. Now, previously, when we were talking about expected returns, by the way, an expected return is our best guess of what the return is going to be. And any expected value is our best guess of what that's going to be. Whenever you hear the weather forecast, that forecasted temperature for tomorrow is an expected value. It's our very best guess of what's going to be. Now, if we are looking at sample standard deviation, we simply use our arithmetic mean of the returns. So we just use the arithmetic mean. But when we get to looking at population things, like we're getting ready to do here, that expected return is going to be calculated in a different way. But they are both going to be the central value of the normal distribution. They are both going to be the central value of the normal distribution. Let me hammer home to you what an expected value is. The year is 1994. I am starting my first job as an engineer, and I'm doing net present value analysis, which we'll get to, and I'm trying to come up with the numbers. And I asked my mentor, who was an Oklahoma guy that always had like a golf ball sized wad of tobacco in his mouth. I said, how do I know these numbers that are going to occur in the future? And he says, you don't. That's how people with tobacco in their mouth say, you don't, meaning you don't. I said, well then what the hell am I supposed to do? And he says, take a swag at it. Swag is an acronym. Does anyone know what it means? Very good. It's a scientific wild ass guess. Now, before you get too excited about my use of the word ass, we're talking about a donkey here. A wild donkey, right? Wild ass guess. Now, what a wild ass guess would just be pulling numbers out of thin air. He says a scientific wild ass guess is when you take what you know to make an informed guess. He says, do you know nothing? And I said, of course I know something. He says, good. He says, use that something to make a swag. A swag is an expected value. Swag is an expected value. So this expected return is our swag. It's our scientific wild ass guess of what the return is going to be on that particular security or portfolio. Okay, then we've already talked about variance and standard deviation as measures of risk. Another word for risk is volatility. Volatility. So you can use, in the stock market, you can use volatility and risk interchangeably. And our measurement of volatility is going to be standard deviation. Now, we mentioned that variance could be used, but the units are screwed up and we can't interpret the number, so we're going to stick to standard deviation. So far, we haven't entered into any kind of new concepts, but now, because we're talking about more than one thing, and we already talked about the interpretive dance, by the way, this is the second time, right? We're going to have this difference in movement between these. And it turns out the more different that movement is between them, the more risk we can get rid of through this thing called diversification. And so we need a mathematical measurement of how these things move with respect to each other. And we're going to have two measurements that we talk about here for how these things move with respect to each other. The first is called covariance. And the second is called correlation. The second one is called correlation. And I am going to teach you how to calculate each one of them. Any questions so far? Okay. Now we're just going to go over this in a we're not going to do any calculations today, but we just want to talk about these two stocks and what might be the relationship between them. First of all, I want you to notice that we've got two stocks. We've got Supertech and we've got Slowpoke. And I want you to notice that we have 4 states of the economy, and that those are the same 4 states for both. And what are the 4 states of the economy? We have depression, we have recession, we have normal, and we have boom. Let's talk a little bit about what each of those things mean. The only one up here that we have that is scientifically determined or defined is recession. A recession is more than 1/4 of negative GDP growth consecutively. So if you've got 2 or more quarters of the economy shrinking, that's considered a recession. And I say that was considered a recession because that was always the measure right up until the last one that we had, when suddenly they're like, oh, maybe that's not a recession after all. Well, we need to change the definition of recession then and go back and rename those other things if they weren't recessions. Okay, so that's recession. The chance of recession here is 0.20 or 20%. You see that in the next column. Now, depression. Depression is like recession, only worse. Do we have a scientific definition of depression? No, we don't. Ronald Reagan, one of our greatest presidents, he once said, a recession is when your neighbor loses their job. A depression is when you lose your job. There's really kind of an emotional feel for the depression, and you know it's got the name depression on it, so you know it's got kind of emotional stink to it. Then we've got normal times. What do you think normal times might be? Just the normal thing we would expect, right? And so we expect in normal times, we expect inflation to be about 2%. We expect GDP anymore to be around 3% GDP growth. So those would be normal times. And then we'll have boom times. Boom is when you're growing faster than normal. Boom is when you're growing faster than normal. Now, I want to point out a couple of things here. Look at the percentages for each one of these. The first thing is that they all have to add to 1. If they don't add to 1, you've got a problem. They all add to 1, which means that we have every conceivable possibility covered in this chart. If we have every conceivable possibility covered, guess what? We're now dealing with population statistics, not sample statistics. That's the first thing I want you to see. The second thing that I want you to see is that those probabilities are the same for both stocks. These stocks are operating in the same economy. They are undergoing the same depressions, the same recessions, the same booms. They're undergoing the same things at the same time. Okay, now let's see how these different stocks react differently. First of all, I'll look at Supertech. During depression, it's down 30%. Makes a lot of sense. Depression's bad, right? And during a recession, it's down 10%. It makes sense that a stock price would go down during a recession. During normal times, it's up 20%. And during boom times, it's up 50%. And so this might be what we would call a normal or luxury good. Normal or luxury good. Could be either one of those. Normal or luxury good. Now, let's talk about what kinds of things Supertech might be selling. Supertech could be selling luxury automobiles. What do you think happens to sales of BMWs when we're in a depression? Way down. Does anyone truly need a BMW? No. You could get by with a Chevy Cobalt. Don't want to, but you could. Okay, now, it makes sense that their sales would be down in a recession, and then it makes sense that they'd be way up in a boom. Does that make sense? Now, let's talk about Slowpoke. In a depression, the return for Slowpoke is 0. Now, a lot of you would say 0, that's bad. Compared to negative 30%, that's flipping amazing, right? Does that make sense? Okay, so far we already know there's a difference. And in recession, this stuff's actually up. And then in a normal time, it's still up. In a boom, it's actually down. And so if I had to guess, the product being sold by Slowpoke is an inferior good. Inferior good. Inferior goods are ones that people purchase more of during bad times. Example, ramen noodles. Tasty but cheap, right? When times are really great, do you say, let's have ramen noodles? No. Cheap alcohol. Do you think when times are great, you're like, let's get out the rot gut? No, you're like getting the good stuff, right? And so those are the kind of products that I suspect Slowpoke might be selling. And so we'll start here next time, and we'll talk about correlation and covariance.